first of what has been covered and also tell you about the total course. Um, an overview of what is robotics was discussed first, and then robot anatomy was discussed in some detail. So, which included mechanisms, actuators which correspond to the muscles, transmissions for transmitting the motion from the motors to the joints, and then sensors which are required for feedback to tell the robot what its state is, and controllers which are used to control the robot. So these are things which have been covered under anatomy. And after that we started on this last topic called robot control. We started with specification of tasks and how motions can be specified or calculated at the joint level. Right? So there are certain calculations which need to be done for control apart from motion calculation. That is what I'll concentrate on, and the two important topics there are position and velocity calculations. So we'll have 2 weeks on that. I'll get into the details of that soon. After that we discuss what can be called as intelligence in robots. Right? So essentially path planning, and after that only we get to the lowest level of control where the robot motors are controlled at the lowest level in order to carry out the motions which are specified. Then a very important sensor of robots will be discussed, that is vision, cameras, and how image processing takes place in typical robot problems. And that will be the details of robotics. Then we'll deal with some advanced topics and also some case studies. So what I'll be covering in the next 2 modules, next 2 weeks, are these calculations, simply these calculations for position and velocity. Fine. Let me motivate why such calculations have to be done. So I'll pose a problem. Consider that some block has to be picked up from some level and placed at some other level. Fine. This has to be picked up by a robot with a gripper. So let's assume we have specified the initial some positions of the robot or rather the gripper. So naturally the gripper has to close onto the object at this position, and finally when it takes it here, it has to release it. Fine. Now in order to ensure that this is taken up and not into the table, into the surface, we may say that immediately after this has to go up. So maybe to a position like this. And before it is put down, to ensure that it doesn't come and hit the corners, it has to be taken up like this, and so we will specify some point here, position here, so that this could be the first position, second, third, and finally we put down the block and release it. Right? When we give these specifications, in order to make the robot move from position 1 to 2 to 3 to 4, we need to calculate what would be the joint angles or joint positions, so that we can control motors in order to make the joints follow those variations of joint angles with respect to time. This is what you learned as joint interpolation, right? So in joint interpolation, with respect to time, let's say you specified time starting from t1, t2, t3, t4, which correspond to these 4 positions, right? And you have calculated at each of them what are the joint angles. So this is some theta 1, some joint angle of the robot varying with respect to time. Now the question is, how do you get these thetas? How do you get the thetas which will make the robot take the end effector, the gripper, take it to position 1 to 2 to 3 to 4. So if I draw it at some position, imagine that this is the robot. Fine. How do you calculate these joint angles? Yeah, this particular problem is called the inverse position calculation problem in robotics. So given the end effector position, determine the positions of the joint angles, values of the joint angles, or joint, it may be a prismatic joint, in which case the extension of the joint, such that the gripper is placed at the position you specify, right? So one problem is you will realize that in order to calculate the entire path or entire trajectory of each of the thetas, you need the thetas at least at these points. Only after that can you do this joint interpolation. Fine. So this particular problem is called inverse kinematics or inverse position problem. Now consider another problem. If you remember, we had taken it to position 1 to 2 to ensure that it doesn't collide with the table or the surface on which the block is kept, right? And immediately before putting it at 4, we had specified a position 3 to ensure that it doesn't dig into the table when it places something. But how are you sure that these joint angles which are calculated will ensure that there is no collision in between? How do you ensure that? So imagine that this computer which is controlling the robot is there. How do you program it to check this? Right, the constraint is that it shouldn't, no part of the robot or the end effector or the object should go into this region, right? So how do you check that? Now you are really talking about how to find this particular trajectory of each of the thetas such that it doesn't dig into or collide with the other objects, right? The problem I am posing is not that. Assuming that we have done a joint interpolation the way it was discussed in the previous module, where we have got now the thetas at every point of time from T1 to T4, right? How do you check whether any collision happens? By doing simulation. What do you mean by that? Yeah. So basically we have to check for every theta, every time, every point of time from T1 to T4, for the corresponding thetas, what are the positions of all the links, and whether the material parts of those links are colliding with either each other or any part of the environment, right? We need to check. What you mentioned would be corrections if we find that there is a collision. We need to then correct this particular trajectory which we have got and take care of that, right? That is actually a higher level problem. We are now looking only at that. So this requires the ability to calculate the positions of the links given the joint angles. This is called the forward problem in robotics. That is, so these two problems are very crucial to controlling the robot, and calculations which these two problems have to be solved for the manipulator for which the controller is designed. You have to have algorithms which calculate this, right? So now let me pose the problem in full detail, and let us formally state these problems so that we can solve them. So the forward position problem is the following. Fine. So there are certain terms here which are not very clear at this stage. One is what are these fixed parameters? What do you mean by joint variables? Even more fundamentally, what is meant by position and orientation of a link? These are terms which are not very clear. Maybe in a simple planar setting it is easier to understand that, but in a spatial mechanism things are a little more involved. And we need to also finally determine the solution. We need to do this calculation. So that is what we are going to discuss in detail. Let me just write down the inverse position problem also. So same thing as this. Fine. It's clearly one is the inverse of the other. That is, what is given in one and what is to be determined are switched here, right? With one difference, that is, here positions and orientations of all links have to be determined from the joint variable values, whereas here given the end effector position and orientation, and you are not given the positions and orientations of all other links, only the end effector, you need to determine the joint variables. So there is some subtle difference here. Fine. So same things are not really defined. These things are not defined yet. So let us first start to do that. But before we do that, let us have you completed writing? Yeah. So before we do that, let us actually pose the problem in a very simple setting and solve it. So we'll look at some simple planar manipulators and solve this. So a 2 revolute planar manipulator with 3 links. So what are given are the link lengths right? And the joint angles theta 1 and theta 2. You need to determine the position of the two links, right? So maybe if you determine the position of B and the point P, you know where the links are, right? So determine, let's call this as global reference frame. So in this global reference frame, the coordinates xb, yb, that is the position of B, and the coordinates xp, yp, position of P. Is that all? The orientations of the links. So let me call them as alpha 1, alpha 2. I mentioned there are 3 links. Which is the third link? The ground. Fine. So what is the calculation? It is very straightforward and simple. XB is that is L1 sin theta 1. What about XP? Plus L2 yeah. This is fine, fairly straightforward and simple. So similarly YP. Now let us look at the inverse problem. So in the inverse problem, in some reference frame at which the pivot of the first link is, ground pivot is, we give the position of P. In addition to that, we also know the link lengths. We need to calculate theta 1 and theta 2. Before we go on to that, let me just check out one thing. We said we need to calculate in the forward problem. This is problem 2. In the forward problem, apart from the positions of the points B and P, also the orientations of the links, right? So what is alpha 1? So I haven't defined alpha 1. So we will say the angle made by the directed segment AB with the x-axis is alpha 1. So that will be the same as theta 1. Angle made by the directed segment BP with respect to x-axis is alpha 2. So what is alpha 2? So that is fairly trivial. Fine. So now the inverse problem is, given the position of a point on the end effector, the tip, find out, and L1 and L2, the link lengths, find out theta 1 and theta 2. So I'll do it here. It's fairly simple, the calculation. If you draw the mechanism in some position and also connect P to A, this is B, right? This angle can be easily calculated because we know the position of P, correct? And now look at this triangle ABP. All sides are known. So this angle also can be calculated, right? So this angle minus this angle will give me theta 1. Fine. Once I have theta 1, I have the position of B, and I have this directed segment BP in this coordinate system. So I can find out alpha 2. Once I find out alpha 2, I subtract theta 1 from it to get theta 2. So let me write it down. So that is this angle. Fine. Then I use the cosine rule. As follows. This is the side L1 and this is the side L2, and this side is the distance from here to here, right? So if I use that, I get L1 square plus you agree with this? Just the cosine rule. Yeah. A tan is the Fortran function for inverse of tan inverse, and A cos is the Fortran function. Fortran, most of the languages have that terminology. So that is one thing. The other thing which should be noted is that this angle A tan inverse is normally known to within 2 quadrants. You don't know exactly which quadrant it is if you use A tan. But we know exactly where yp and xp are, what yp and xp are, and so where this particular point P is, in which quadrant it is. So we can actually precisely calculate this angle, including the quadrant in which it is, and there is a function which gives you that, which takes 2 arguments. It takes it is called A tan 2 in most of the languages, and you give 2 arguments, yp first and xp next. So if you use A tan 2, you get this uniquely. Otherwise, you get 2 solutions for that. This is one point. The other point is about this particular angle. How many solutions are there for this angle? Inverse cos. If you get some 30 degrees, minus 30 degrees also will be valid. There are 2 solutions, right? And both the solutions are valid actually. If you look at the other solution, it is this. So this could be minus or plus. So the inverse kinematics problem here has 2 solutions. This is very important to note. Is it that in every case there is 2 solutions? There are 2 solutions. It can be more than 2. I am talking about this particular problem. Yeah. Well, there is a particular case where it can be more than 2. It can be infinite. But let me first ask you the other question in the other direction. Can there be less than 2? 1 can be there. right? When it is stretched out, for example, if the point P is given as some point on the boundary of the workspace, right, then there can be only one solution. Yeah, it can be, but suppose it is outside the workspace, there cannot be any solution. How will it should show up in our calculation, right? When we say there is no solution, one solution, two solutions, infinite solutions, it should show up in this particular equation that we have written. Where does it show up? Right. Cos inverse argument has to be between -1 and 1. If it is outside that, then there is no solution. And the function is not defined outside that domain. And if it is 1 or -1, there is only one solution, right? If it is 1, you can have only 90 degrees as a solution. If it is -1, and sorry, if it is 1, you can have only 0 as a solution. If it is -1, only 180 degrees as a solution, right? In these cases, there is only one solution. And if it is less than -1 and greater than -1 and less than +1, there are two solutions. Okay, these are the ways it occurs, and you can recognize it from this calculation directly. Another point that one needs to notice here is the following. I said that in the definition of the problem of inverse kinematics, if you look at this, the position and orientation of the end effector was given, right? Whereas if you look at the way we pose the problem here, what is given here? Only the position of a point on the end effector is given. The orientation is not given. Can you figure out why that was done? Right, that is correct. But more generally, the answer is this is a 2 degree of freedom mechanism. You cannot specify 3 position variables independently. The third one will be dependent on the other 2. So you cannot give arbitrary specifications for the position of a point on the end effector as well as the angle made by the end effector. Okay, that is why only this was done. So now let us go back to some of the things which were not fully defined when we stated the problem. We said that something called fixed parameters of the mechanism has to be given. What are the fixed parameters here? L1 and L2, right? Those are fixed. Any other fixed parameter? Ground is fixed, but what about the parameter? I could have actually positioned this anywhere here, right? So location of the point A in the global reference frame really is a parameter, can be treated as a parameter. Here I actually simplified it by putting the origin of the reference frame right at the point A. It needn't be the case. Okay, so if I had put it here, XA and YA would also be some fixed parameters. Okay. Now what about join variables here? Theta 1 and theta 2 the way it is given here. But why did I define theta 1 and theta 2 this way? Why not use alpha 2 instead of theta 2? Easier to find, but I suppose the calculations would be as simple. Alpha 2. Yeah. Right, the actuator is mounted on the link, and if you think about the control problem, it is the motors that we have to rotate in order to make the joints rotate, right? And joints are going to rotate, the angle the joint rotates by is essentially the angle by which one link rotates with respect to the other. That is why the angle is defined as joint variable is defined here as an angle made by one link with respect to the other rather than with respect to the base link. So the angle between the two links which are at the joint. Okay, so these are things which we will do in a more systematic way when we go to specifying this for spatial mechanisms. This is a fairly simple planar mechanism case. So let me come to the 3R manipulator which you mentioned and pose this problem. Anything else to be determined here? Theta 1 has been determined. What about theta 2? That also has to be calculated. How do you do that? Yeah, we know alpha 2. No, do we know alpha 2 right now? We don't know. We have to calculate it. How do we get that? We know theta 1 now. We can find out what B is, where B is. Once we know where B is, we can find out the angle BP. That is alpha 2. Once we get alpha 2, subtract theta 1 from there, you get theta 2. That's clear? I didn't write it here. So let's look at the 3R manipulator and pose this question. I will pose only the inverse kinematics here. So given the link length, so let me show it first and then set up the reference frame. I put an end effector at the end so that orientation becomes relevant. And let me consider a point on the end effector, although it appears to be not on the end effector. Can you see clearly? It is not on the end effector. This is some point fixed with respect to the end effector. Fine. The link lengths are L1, L2 and L3. The joint angles define the way we have defined earlier. So what is given here are these link lengths and the fact that the end effector, this special point P, so this is A, B, C, this particular point P on the end effector, which is typically called a reference point, which was used for defining workspace. If you remember, reachable workspace was defined using a point on the end effector. Right? So this particular point P is here, and the direction of the link has to be this, which essentially is given by this angle. So position of P and the angle alpha are what are given. So L1, L2, L3, XP, YP. Let us call it alpha 3 because this is the third moving link. Alpha 3, right? We need to calculate theta 1, theta 2, theta 3. So this is the point P, and this is the direction made by the vector Cp, right? Alpha 3 is the direction made by vector Cp. How do we now calculate the joint angles? Right. This is the same as before. Did you hear that? The suggestion is that we know the position of P and the direction Cp. right? With this information we can calculate the position of C. How do we do that? Geometrically draw this, extend this line backwards by distance L3. No need to cut an arc. Measure this out, so you get the point C, so that this distance CP is L3. The remaining part is the same as what we just did for the 2-hour manipulator. This is as simple as that. Fine. Though simple, this is actually one of the crucial steps in even the more complicated manipulator. This is something we will do even in the more complex manipulator, because of a particular property of the kind of wrists which are used in these manipulators. Okay. Is the procedure clear to everybody? I'll just write it down. Fine. So from XC, YC, L2 and L1 we can calculate theta 1, theta 2 as we just now did, right? And theta 3 is nothing but alpha 3 minus alpha 2, right? And alpha 2 is theta 1 plus theta 2. Fine. So it's as simple as that. So again the question of how many solutions? This is a crucial question in in all the problems. 4, 1, 2, 3, 4, 5, 4, 2. Yeah. Why 2? Why not 4? No, alpha 3 is given as an angle for the direction of CP. That is a unique angle. So it can only be, CP can only be in that direction, then only 2, right? Because this has only 2 solutions. This is unique. So we have already found that this is 2 solutions. Can there be a case where there is 1 solution? There could be. And no solutions? That also is possible, right? But that will show up in this calculation. Fine. But the case of no solution, it is important to realize, may not be a point which is not reachable. There could be a point which is reachable by the position, there could be a location which is reachable by the point P, but still there may not be a solution. The reason is that we would have specified a angle alpha 3 which the link should have when the point reaches that. So imagine that the whole thing is stretched out, let's say in this direction, then CP can only be 0, right? The position is XP equals L1 plus L2 plus L3, right? YP is 0, somewhere over here, right? YP is 0, and angle, if anything other than 0 degrees is given, this is not possible, right? A little inside you will find that only a range of alpha 3 is possible. In fact, you would have studied that Dexter's workspace is one in which this particular point P can reach with all orientations possible for the end effector, right? So there are points in the reachable workspace which can be reached, but you cannot orient the end effector any way you want. That is restricted. This shows a case like that. But I told you about a case where this particular manipulator's inverse problem has infinite solutions, and I didn't really describe what that is. Right? Assume that L1 is equal to L2 and XP and YP are 0. Right? So this gets folded in and P coincides with A. We are demanding that P should be at A. So all that is required is that the angle theta 2 should be 180 degrees. Theta 1 can be anything. Correct? So this is a case where there are infinite solutions. So such funny things can occur. Okay, so these problems are fairly simple. We should progress to more demanding problems which involve spatial kinematics. But let me introduce one problem which is fairly simple even if the mechanism is spatial. This is a Cartesian manipulator with 3 prismatic joints. They are orthogonal, mutually orthogonal directions for the prismatic joints. So let me locate it in a very simple fashion. So one link moves along this, that carries another, which so X, Y and Z. You have understood what the manipulator is. This is the base joint. This link can slide along that, taking this entire structure along with that, mechanism along with that. On this there is a member which is perpendicular to that, slide perpendicular to that, horizontal again, and this particular slide can slide on that, translate, and on that there is another link on which this link can slide up and down. Fine. Let's assume this particular point P is XP, YP, ZP. The location of this point on this in this reference frame is given. What do we need to find out? Any fixed parameters of the mechanism? Well, there are some fixed parameters, but let us not worry too much about that. Let's see how to solve this. Right? Those will be defined later. We need to find out what the joint motions are, positions are. So let me call it, let's say S1, S2, S3, where S1 is the distance by which this particular link has moved from the origin. S2 is the distance by which this link has moved from this point, and S3 is the distance by which the point P has moved above this particular point. Fine. So the question is, what are the values of S1, fairly straightforward. This is xp itself, correct? If I define the joint positions like that, S2 is yp and S3 is zp. Why did this simplification occur? Because I oriented the the global reference frame axis along these convenient directions. So the whole problem was very simple to solve. So we should make it a little more complex. What we should do is orient the global reference frame in an arbitrary fashion or in some other way. So let this be x, y, z. The joint variables are still S1, which is the motion of this, position of this with respect to some initial position, position of this with respect to some initial position, and position of this with respect to some initial position. So those remain the same. So we can actually solve it a little later when we define orientations and things like that. Fine. But this appears so simple and trivial, can be complicated by a small change. Okay. So we'll try to solve it later. Yes, that is very true. Yeah. So now in order to, we had defined the problem of forward and inverse kinematics, and we have now seen two planar mechanisms which are fairly easily solved, and one spatial mechanism which is easy if we set up the reference frame in a particular fashion. Fine. Now we need to look at spatial manipulators in its generality, and in order to do that, we need to define some of these things which were left undefined. We have to define them. So what we will first take up is the idea of position and orientation. How do we define position and orientation of rigid bodies? Fine, you have done a bit of this when you did engineering mechanics or a corresponding physics course, but we will do it formally now. Any questions here? Which means you have understood everything. Shall I ask questions? Yeah, let us look at this concept. So we will do it only for rigid links. So what is meant by position of an extended body, like this book for example? We can talk about positions of points, right? That is easy to talk about. We set up a Cartesian reference frame, rectangular coordinate system, and specify positions using that. Position of a point is easy to define, but a body has infinite number of points, right? Do we have to specify the position of all those points in order to? So so what exactly is the concept of position? We can define very clearly position of points. is fairly easy to define. So if there is some body, take a point on that, what the position of that point in a global reference frame is a fairly simple concept, right? And as the body moves, the position of that particular point, let's call it P, that changes. Okay. Similarly, what about orientation of a body, an extended body? We can talk about directions of vectors. That is something we are familiar with, right? So we need to, what I'll try to do is try to relate position of bodies and position of a body, and or rather position of points on a body and directions of directed lines on a body to the idea of position of points and directions of vectors. These are simple concepts. For example, if there is a vector on this body, we have drawn a line with a direction, fine. That particular vector can be translated here with its tail coming out here. The coordinates of the tip can represent a direction, fine. It could be any vector of any size in this direction that can represent the direction. Typically we take unit vectors. Okay. Now actually, instead of asking what is position and what is orientation of rigid body, we should really try to figure out why are they useful. Fine. What is it that we need to specify? How do they become useful? So let us look at a typical situation where a robot works and see whether something like this is useful. So one case is, take a pressure vessel which is welded out of sheets and some dished ends, fine. You need to form this weld, right? Weld the two edges of the sheet together and weld the ends to that, and you need to do it with a robot. How do we specify how the welding gun should move? We have a welding gun. This is attached to a robot. This would move along this, right? How do we specify that? Yeah, the path that should be taken by a point at the tip of the weld gun, we can specify that. That should be along this particular line. What else should we specify in order to make the robot do this work? The speed with which it should move along that. So in addition to path, I can say trajectory. The trajectory of the tip of the welding gun along this should be specified, which includes velocity. So the time information also is known. What else? What about the orientation? Maybe we should keep the tip a little away from that hot zone, not the tip but the rest of the gun away from that hot zone, right? So we can probably orient it slightly in one direction. So we may specify that this particular vector which specifies the vector which is axial to the gun should be in a particular direction, right? These are things which we should typically specify. But the gun can still rotate, keeping the point right there and keeping this orientation for the final part. The gun can rotate about that particular axis and still maintain the orientation which is important to us, and also maintain the position of the tip. correct? I am talking about, let's assume the one gun is like this, and I am saying that this tip should be at this particular point, and the orientation of this particular axis of the of this particular tip, or this part of the gun, should be in a particular direction. But I can still rotate the gun about this. I haven't said that that should be locked in a particular position. Maybe it is not important to lock that. So it depends on the specific situation. Suppose we want a robot to fire a gun, right? What is important is that the gun barrel points towards the target, and that can be done without actually specifying everything. Okay, so this is one example. Another case with which I will stop is consider an assembly problem in which there are certain recesses here, into which small projections on some part has to fit. The part, let's assume, is like this. So I am showing it from one side. So there are some small projections here which have to go into these holes, right? This is an assembly problem where we pick up this part and we bring it here and we insert it as snap fit. Now, in order to specify where the part has to be brought on top of this before we start the insertion operation, what all do we need to specify? Position of one hole. Okay, if we specify position of one hole, let's say one peg, let's say this hole position is specified. So this particular point on the peg or on the projection will be brought here. Okay, then what? One vector direction. So now you are saying 2 points. So let us take 2 points. So I take this particular point. So this center of this particular peg will have to be poised on top of that hole. Correct? Is it sufficient? Not sufficient? Right, because once you position these 2 points in space like this, I can rotate the whole body about this line, right? So we need to figure this out properly, right? And this, the way the operation has to be specified for bringing this part on top of this and insert it can perhaps be specified in many ways. So all this has to do with positioning of points on the body and directing vectors on the body. That is why I said these are the 2 important things, and using this we can arrive at a specification of position and orientation of extended rigid bodies, which has infinite number of points and infinite number of vectors on the body. Okay, so we will do it in the next class, but before that let me recapitulate. What we are tackling in the next 2 modules are calculation of positions and velocities of rigid bodies, especially interconnected rigid bodies. Manipulators are made of interconnected rigid bodies. So we will develop a formalism or a set of tools with which we can do these calculations. This will be useful not only for manipulators but also for mechanisms in general and spatial mechanisms. Fine, we will meet in the next class.